is and what we do, but I'll touch on that. And then I want to touch on how we engage our stakeholders, and then talk about our approach to our energy footprint and greenhouse gas emissions and some of the innovative work that we've been doing in this area. So we could go to the next slide. So let's start with who and what American Water is. Many of you probably know who we are. We're the largest U.S. water and wastewater provider in the area. We serve over 14 million people and businesses. The company dates back to 1886, and I'd like to say, even though we don't have any wooden pipes anymore, that we do have some pipes that are still in service today that date back before 1900, and so some of the utilities on the line probably have that similar experience. We can go to the next slide. I want to talk for a minute about our stakeholder engagement and how we do that. We use many different tools to reach out to our stakeholders. Like many of you, we have a website and social media that we use to reach our customers. Bill inserts obviously are a good traditional way to reach your customers. We also hold customer roundtables and surveying to find out how satisfied our customers are and to educate them about the value of water and that water-energy relationship. We also have in our construction program, when we do major projects, we have communications plans around those construction projects so our customers know what we're doing, the community leaders, regulators, and the general public can follow the progress that we're doing to the improvements of our water systems. Many of our messages have to do with water efficiency and energy efficiency, and you can see one of the quotes I put on the bottom of this slide is from the EPA WaterSense, which we're a partner of, that if 1 out of every 100 American homes was retrofitted with water-efficient fixtures, we could save about 100 kilowatt-hours of electricity per year, avoiding 80,000 tons of greenhouse gas. So what we try and do is use those types of quotes from across the industry on our website and in our communication with stakeholders to show that your water use also impacts electricity use and greenhouse gas emissions. So let's go to the next slide. American Water has received recognition for our corporate responsibility engagement, and I thought I'd talk for a minute about what that looks like. We are part of the Dow Jones Sustainability North American Index. We've been recognized for our corporate responsibility, and a lot of that has to do with our approach to reducing greenhouse gas emissions. We've set goals for that each year, and we issue a corporate responsibility report as well. We can go to, before we go to the next slide, I did want to point out the graph there, the chart on the slide there. You can see that in that pie chart, when we study our greenhouse gas emissions, 92% of that comes from our use of electricity. And anybody who works in the water, wastewater area certainly knows it's not a surprise that it takes a lot of energy to pump water and to clean water. So we can move to the next slide. Okay, there we go. We really have a three-part approach to how we look at the energy-water nexus. The first part being, how do we use energy? We measure our energy usage through an energy usage index, which quantifies the megawatt hours of power used per each million gallons of water we treat and send to our customers. So we have several different tools in that toolbox to help manage our energy usage. The second part, which I will only touch on briefly today because of the time limit, is around water efficiency and what we can do in that area. And the third piece is around climate variability risk. We really don't have time to talk much about that today, but certainly that is part of the whole water energy nexus discussion. We do comprehensive planning work for each of our water and wastewater systems, and we look at resiliency of those systems. So that's a big part of what we do and the stakeholder engagement that goes along with that. We can move to the next slide. So I want to spend a few minutes talking about how we use power and what we're doing in that area. We've deployed over 3 megawatts of solar capacity at 3 states in the last 10 years. Our first application is just coming up on 10 years of age. And so we've done traditional solar fields, but you can also see in the picture here we've done some innovative approaches. At one of our reservoirs in central northern New Jersey in Canoe Brook, we've constructed, we call it our floating solar field. It produces about 135 kilowatts of solar power. It's a small percentage for the whole plant, but it's an innovative application that we were testing out to see how it would hold up in the cold weather climate that we have here in New Jersey. We also, in the small picture over on the right, is a mixer, a solar-powered mixer that we use in some of our reservoirs. And we've really been looking at different applications to use solar power. One of the interesting ones I don't have a photo of, but when we have remote tank sites that we're trying to make sure that we keep our SCADA signals live during storm events, when trees fall down and take power lines out. We've used small solar panels with battery backups to make sure that we always have those tank level signals coming in. So there's a lot of different types of smaller applications of solar that get us off the grid, provide us with green energy and some resiliency at the same time. We can go to the next slide. I spoke earlier about our greenhouse gas emissions, and we know that through a study that 92% of our greenhouse gas emissions come from electricity, and predominantly that's from pumping water. So a lot of our focus has been on how do we reduce that energy footprint? How do we make our pumps more efficient? What you see here is part of that study. We look at the life cycle cost of pumping, and you can see in the green there that 85% of the life cycle cost of a pump is in the energy usage, with the capital cost being a much smaller increment. When we look at new pump stations, and you look at what we call the wire-to-water efficiency, and that means how much electricity or how much power do we need to put in to pump 1 gallon of water. When we look at that, you would love to see that as 100%, but that's not possible from motor efficiencies and pump efficiencies. So when we look at newly designed facilities, we're up around the 80%. When we look at aging water and wastewater pumping, that can fall down to 45–50%. And so that's a good opportunity to rehab, to work on those pumps to gain some energy efficiency back. We can move to the next slide. So what are we doing in terms of looking at our pump efficiencies? There's a number of different things that we can do. We can replace inefficient pumps. We can work on the insides of pumps, trimming what's called an impeller. We can even spray on a smooth coat, a new finish inside the pump to take away any kind of friction or energy loss within the pump. We can look at variable frequency drives and rehab the pumps as well. So all of those different tools we have available to us to help improve the efficiency of our pumping. If we go to the next slide, again, I have a few examples of what kind of magnitude we're talking about when we look at rehabbing pumps and replacing pumps. Here's an example from our Virginia American system in Hopewell, Virginia. And a few years ago, we replaced one pump and we installed a new pump. And what we have plotted here, we measure our energy usage per million gallons pumped over time. And you can see that while it has a slope, while the line has a slope to it, that it's improving, really we have kind of the before level and then it drops down to a new level. And overall, we've seen with just replacing that one pump and adding a more efficient, smaller pump, that we've gotten over 10% reduction in our energy usage for that state. We'll move to the next slide. Staying in the area of pumping and energy and electricity efficiency, I want to talk for a minute about one of the innovative approaches that we take. We have an innovation development process within American Water, and one of the first things that we've deployed is our partnership with AMWA, which is a provider that helps us work with the energy grid. When there's tremendous use out in the energy grid, AMWA will work with us, and they can actually control our pumping so that we shave some of those peaks so that we're not on the grid. And it's it's not noticeable to our customers, it's not noticeable to our operations, but it allows us to shave kind of micro peaks, if you will. And our first pilot with that in PA showed that we got a 2 to 3% reduction in our total energy bill for that facility. And as a result, we think that this is a very promising technology, and we're in the process of deploying it at several other locations. We'll move to the next slide. Another example of what we can do in the energy footprint is looking at our infrastructure, looking at our piping infrastructure. Here's an example of a scenario where we put in a new transmission main in one of our systems in New Jersey American. And what you can see plotted here is again, on the y-axis, energy usage per million gallons of water pumped. And on the x-axis there is the pumping rate at the plant. The blue is before this new transmission line, and the red is after the new transmission line at the same pumping capacity. And so overall, we were able to reduce our energy usage index by over 20% for that facility. Certainly, building a large transmission main like that takes a lot of stakeholder engagement, and I've noted some of the folks there that we worked with throughout that process. Okay, moving to the next slide. I won't spend much time on the next two slides, but I wanted to just highlight to you some of the other new tools that are out there that can help us deal with aging infrastructure. And aging infrastructure and leakage from pipes touches on that water efficiency parameter in this water energy nexus discussion. So one of the things that we're looking at and we've deployed are some new tools to figure out the remaining pipe wall thickness of our water mains, and that's going to help us when we look at making improvements within our system. So that's one example. If we go to the next slide, we also have deployed newer technologies to find leaks. And this is an example of something that we were doing in PA. There's even more in different technologies that we're deploying, but they again help us. If we find leaks, we can repair them sooner, and that helps our water efficiency. Going to the next slide, I want to spend a minute talking about wastewater. So far we've talked mostly about water, but I want to spend a minute talking about the innovative work that we're doing in wastewater. We have a number of smaller wastewater plants that use membrane bioreactors, and we've used this process that we've actually gotten patents for. We call it the MP Express process, that has allowed us to reduce the amount of oxygen, reduce the aeration phase, and really not add as much carbon supplement. So that helps us twofold in terms of costs and energy. It reduces our energy cost, and it reduces how much carbon we have to add to the process. I won't go into the microbiology here, but it is a simultaneous nitrification, denitrification process. And if anybody would like to learn any more about that, you're certainly welcome to contact me after this webinar. We'll move to the next slide. And I want to talk for a minute about reuse. and what we're doing in the area of water reuse. So water reuse is taking wastewater, treating it to a higher level, and using it in a different application. Here, this was one of our early reuse projects in the Solaire building in New York City, where we're collecting the wastewater, treating it to a high level, and then it's used within the building for flushing toilets and cooling water and landscape irrigation. In this facility, we also deployed the NP Express process, and we see tremendous energy savings there. And with that, we can go to the last slide, and I thank you all for your attention today, and I will hand it back to you, Joe and Erica.
Great. Thank you, Suzanne. That was excellent. And we're going to jump into one of our poll questions. Okay, so the question that we'd like to ask is, Suzanne shared quite a few different types of kind of innovations and technologies that a utility might deploy. And we're curious, for those on the line, which would be of most interest to you, whether those related to renewable energy, the repair or replacement of existing infrastructure, trying to do water or energy audits, or looking at kind of demand side issues. Folks could just take a couple seconds and click on the one that resonated the most. Okay, I'm going to close the poll, and this time hopefully I'll successfully share it, which I didn't do last time. There we go. Okay, so renewable energy and water and energy audit seems to be kind of the leaders of the TAC, which I think is excellent. The audits one in particular is excellent given what we have coming for our next presentation. So with that, I'd like to turn things over to Erica.
Thanks, Joe. It's my pleasure to introduce to you Clifford Chan from East Bay Municipal Utility District in California. For the last 7 years, Clifford Chan's been managing the operations of East Bay MUD's water treatment and distribution system. He's been at the district for 17 years. He's worked in both the engineering and the operations departments. And prior to joining East Bay MUD, he was a consulting engineer and worked on a variety of environmental and geotechnical projects. Clifford received his undergraduate and graduate degrees from the University of California at Berkeley, and I think his presentation is going to tie nicely with Suzanne's because he's going to focus on a particular thing that East Bay MUD is doing with regard to assessing the utility's energy intensity. So Clifford, the floor is yours.
Can everyone hear me?
Yeah?
Yeah, sounds good.
Okay. Thanks for giving me the opportunity to speak on this webinar. Today I'm going to talk about the water energy nexus. And we know it takes energy to treat water, but it also takes water to produce energy. And few of us consider the energy impact of a leaky faucet, and even fewer people consider the water impact of leaving a light on. Now, one way a utility can reduce its energy use is to implement energy efficiency programs. Historically, most of these programs focused on increasing the energy efficiency of pumps or treatment technologies. However, utilities can also reduce this energy use by implementing water conservation programs. But when developing a water conservation program, utilities typically don't consider how the energy intensity of water varies throughout the year and across the service area. In this presentation, I'll talk about how we developed a better understanding of our energy intensity and how this information can be used to develop a more targeted conservation program. Next slide. This is just a brief overview of the presentation. I'll talk about East Bay MUD, and then we'll go into the water and energy use, then go into detail about the energy intensity study we completed with UC Davis, and finally share with you some of the benefits of the study and next steps. Next slide. East Bay MUD is a public utility that supplies drinking water to approximately 1.3 million customers and wastewater services to approximately 650,000 customers. We're located on the eastern side of the San Francisco Bay. Our water service area is approximately 332 square miles, serving 35 cities and communities. The wastewater service area is smaller, covering an 88 square mile area that includes 6 cities and 1 sanitary district. If you look at the map, the green shaded area is our water service area, and the hashed area is our wastewater service area. Next slide. How we operate our water system greatly affects our energy use and intensity. This map gives you an overview of our service area and our watershed along the western slope of the Sierra foothills in California. The bright green area is the McCallum River watershed. It's a protected watershed with an area of approximately 577 square miles. Snowmelt from the McCallum provides 90% of our water supply. Next. We store water from the McCallum in Pardee and Comanche reservoirs. Next. The water flows from Pardee Reservoir to our service area via the McCallum aqueducts. In many years, the water is conveyed almost entirely by gravity, but because of our high-quality water from Pardee, minimal treatment is required. Next. We also have 5 local raw water reservoirs in our service area. The water quality in those reservoirs is not as good as McCallum and requires full conventional treatment. Next. Finally, in dry years, we can also tap our Freeport water supply, which we've just constructed off the Sacramento River. Water quality from the Sacramento River is not as good as McCallum and also requires full conventional treatment. Next slide. Water-related energy use in California is tremendous. If you look at the energy, it's used for pumping, treating, heating, and cooling water. In California, water-related energy use accounts for 19% of the state's electricity use, or about 48,000 gigawatt-hours. To put this number in perspective, that's the annual energy use of approximately 4.8 million typical residential homes. Water-related energy use also accounted for 30% of the state's natural gas use and used 88 million gallons of diesel fuel. Now, if you look at that 19% electricity use, 4% is used by water utilities, 1% by wastewater utilities, and 14% by the end users. And during droughts, the energy use can increase significantly. Next. This chart shows the energy intensity for East Bay MUD and typical Northern and Southern California utilities. In normal years, East Bay MUD uses about 1,250 kilowatt-hours per million gallons, which is about what the typical Northern California utility uses. However, Southern California uses about 10,200 kilowatt-hours per million gallons. Next. So why is this the case? Next. In California, 70% of the state's total runoff is north of Sacramento. Next. But 80% of the state's water demand is south of Sacramento. Raw water conveyance accounts for most of the difference in the electricity use between Northern and Southern California. Next slide. This table shows a breakdown of energy intensity between East Bay MUD and the typical Northern and Southern California utilities. Next. You'll see that on average, raw water conveyance requires 50 to 60 times more energy for Southern California utilities than Northern California utilities. In fact, 40% of Northern California's population is served by gravity-fed systems, whereas Southern California imports water from the Colorado River and Northern California, which requires quite a bit of raw water pumping. Next slide. Now, our energy management strategy focuses on minimizing our energy use and costs, diversifying our energy supplies, and educating our employees and customers. Next. Because of the strong connection between water and energy, we know that if our customers use less water, we'll also use less energy. Our conservation measures improve customer water use efficiency and includes rebates and other incentives, education and outreach, regulatory programs, and new technologies. But when we develop our water conservation programs, we treat all our customers the same. That is, a gallon of water saved at a home in the flatlands was equivalent to a gallon of water saved at a home in the hills. Next. Now, I've mentioned energy intensity a number of times, so before I go any further, I just want to define the term. Energy intensity is the amount of energy consumed per unit of water. In this presentation, I'm going to use kilowatt-hours per million gallons. Next. For our study, we looked at the outdoor and indoor energy intensity. The outdoor energy intensity is the sum of the raw water pumping, water treatment, and distribution energy intensities. The indoor energy intensity is the outdoor energy intensity plus wastewater collection and treatment. Next. So I'm going to talk a lot about energy in this presentation, but for many of us, it's hard to kind of get a good feel for what the numbers mean. Energy is the amount of power used over a period of time. So for example, if you turn on a 60-watt light bulb for 1 hour, you'll use 60 watt-hours of energy. Calories is also a measure of energy. So to put our energy use in perspective, I converted some of the energy uses into something we're all familiar with, the calories burned when we walk. So if you leave a 60-watt light bulb on for 8 hours, that's the equivalent of walking 82 days straight. Next. Leaving your computer on at work for 8 hours is equivalent to walking for 246 days. Next. And finally, you'd have to walk for 12.5 billion years, or basically start walking when the universe was formed, to burn the equivalent amount of electricity that California uses in 1 year for water-related energy uses. Next. So let me get into the study we did with UC Davis. We wanted to better understand and estimate our energy intensity, so we partnered with UC Davis's Center for Water Energy Efficiency on a research project supported by Pacific Gas and Electric's Emerging Technology Program. Now, this wasn't the first study on energy intensity of water supplies in California. There were 2 previous studies. The first focused on energy intensity of major water transfers in the state. The second estimated energy intensity of a number of water and wastewater utilities in the state, but it didn't look into the reasons for the variation in the energy intensity between utilities. The goal of this study was not only to estimate the energy intensity of water, but to understand the temporal and spatial variability of the energy intensity. Another goal was to develop a framework for calculating the energy intensity in a way that wouldn't become a data management and analysis burden. I should also mention that the California Public Utilities Commission recognized the linkage between energy and water, and as part of their energy efficiency proceeding, identified the water sector as a target for energy efficiency efforts. The state gives rebates for energy conservation programs and was looking for a methodology that could be used to give energy rebates for water conservation programs. But allocating energy efficiency dollars for water conservation savings required a clear, defensible calculation of the energy intensity. And finally, the study supports the state's Global Warming Solutions Act, which requires California to reduce its greenhouse gas emissions to 1990 levels by 2020. Reducing water use is one of the strategies in the state's climate change scoping plan. Next. Going into the study, we knew that there was no one-size-fits-all energy intensity for a given gallon of water. The energy intensity varies within a utility and varies from utility to utility. In order to increase your efficiency, you need a reliable baseline energy consumption. You also need to consider seasonal and spatial effects on energy, since energy use can vary significantly depending on where and when it's used. But installing sub-metering to monitor energy and water flow is expensive, so we were looking for a software solution rather than a hardware solution to estimate energy intensity. The software solution we considered for this study was to leverage existing systems like our SCADA system. The techniques developed could be used as an effective measurement and verification of our energy savings. Next. Now, most utilities have a SCADA system that collects data. They also have billing data with energy use and an asset management system. We wanted to develop a high-resolution characterization of how the energy intensity varies using these existing data sources. For example, the SCADA data can be used to estimate the embedded energy as well as for optimizing operations for energy efficiency. Now, if you join this data to the asset management system and the customer data systems, you could also help with water loss detection. But doing this isn't trivial, and it's part of another study we're considering working with UC Davis on to solve this big data problem. Next. So the first step of the study was to understand how and when energy is used. what you see on the slide is an example of the mapping we had to do with UC Davis for them to better understand our operations so they could develop their framework. What became clear to UC Davis was the importance of understanding all the components and operational strategies in order to accurately calculate the energy intensity. Next slide. The next step required us to get all our electrical use data. The graph that you see shows the electricity consumption for water and wastewater use in the study areas from 2006 to 2012. You'll notice that the wastewater electric use in dark blue and red is relatively flat. There's a bit more variation in the distribution and treatment use in green and purple, and quite a bit of variation in the raw water pumping, which is in light blue. The distribution and treatment energy use varies based on water demand and on the water source used. The reason the raw water pumping varies so much is because it depends not only on the water demand, but also on the water year type. So in a wet year, we may need to pump less because runoff is sufficient to fill our reservoirs. But if the water demand is high, we may need to pump to meet peak demand. Next slide. So once we have the energy use data, we can use our SCADA data to analyze when we operate our facilities. If you look at this graph, it shows our raw water pumping for one of our facilities. Going from left to right on the graph is the time of the day starting from midnight, and going from top to bottom is the day of the year starting from January 1st. The red in the graph means that we're pumping all day. Yellow means that there's some pumping during the day. And green means that there's no pumping in the day. So if you look at our raw water pumping, there's a lag between when we pump and when we use the water. That is, we tend to do most of our raw water pumping in the winter to fill the reservoirs when energy cost is cheaper, and use water in the late spring and summer when water demands are higher. Next. Our distribution pumping is also driven by the cost of energy. You'll notice that in the summer, we almost completely avoid pumping during the higher peak periods. From noon to 6 p.m., and that's the large green block you see in the middle of the graph. And that's also when the energy cost is highest. And we do most of our pumping during the early morning hours when the energy cost is the cheapest. Similar to the raw water pumping operations, there's a time lag between when we pump and when we use the water. That is, we don't pump to demand. Next slide. Next, as part of the study, we looked at our water treatment plant operations. In the summer, when water demand is higher, we have to have all 5 of our water treatment plants in service, and those are circled in red and blue. Next. But in the winter, we can meet all our customer needs with just 2 of our water treatment plants. Next. Now, one of the major reasons we do this is because the cost of operating these seasonal plants is significantly greater than the cost of operating the water treatment plants that are in service year-round. So, for example, if you look at a Rinda water treatment plant, one of the plants that operates year-round, it's an inline filtration plant that costs about $50 per million gallons. And the cost includes electricity, chemicals, and solids disposal. But if you look at USL water treatment plant, that's a full conventional treatment plant with intermediate ozone and costs about $517 per million gallons to operate. Next. So after you collect all this data, the raw water pumping, the distribution pumping, the treatment costs, and our operating data, you can start calculating the energy intensity. And what you see in the graph is that the energy intensity varies quite a bit throughout the year. That black line on the graph shows the average energy intensity by month. And the monthly energy intensity varies plus or minus 13% around the annual average. We also found that in some of the drier years, 2009 to 2011, we had a lower energy intensity because the water demand was lower and we didn't need to do as much raw water pumping. But the variation between water year type wasn't that great. And we do expect that this will change in a prolonged drought if we have to do a lot more raw water pumping from our supplemental water supplies. Next. You can plot all this data on a map and get an energy intensity map. If you look at this map, the blue represents areas with lowest energy intensity and the red areas with the highest energy intensity. And not surprisingly, lower areas, that's areas where our customers are fed by gravity, have the lowest energy intensity, around 400 kilowatts per million gallon, while customers in the hills have a high energy intensity of almost 5,000 kilowatt hours per million gallons. Next slide. This graph shows the energy intensity map along with a graph of the water consumption in the various pressure zones in the study. So for example, if you look at the water saved in the Leland pressure zone, water saved in the Leland pressure zone would save about 500 kilowatt-hours per million gallons. But if you look in the upper right corner, water saved in the Miller pressure zone would save almost 5,000 kilowatt-hours per million gallons. In fact, as a rough estimate, we found that the energy intensity increased by approximately 1,000 kilowatt-hours for every 200 feet of elevation change. But if you look at the size of the bubbles, which is the relative water consumption by pressure zone, there's less opportunity in the Miller pressure zone when compared to the Leland pressure zone. So a better way to look at this is to calculate the total embedded energy. That is, if you multiply the energy intensity by the water consumption, you get the embedded energy. And using this total embedded energy, you can find the energy intensity hotspots. So if you do this, you'll find that our Danville and San Ramon pressure zones are the best targets for initial water conservation projects if you want to maximize energy savings. Next. So there are a number of benefits from the study. First, we have a better understanding of when and where energy is being used. We have a better understanding of how the energy intensity varies throughout the year, across our service area, and by water year type. We can also use the information to intelligently target conservation efforts and infrastructure upgrades. We can set realistic targets for water and energy conservation, and now have a tool to measure and verify our energy savings. Finally, we've developed a methodology that can be used by the state to enable energy efficiency programs for water conservation. Next. As far as next steps, UC Davis wants to reproduce this methodology with some other utilities. They also want to simplify and automate data extraction, manipulation, and analysis, and are looking towards cloud-based computing to help with the analysis. Moving this direction, they're going to have to develop a common data platform. And finally, we're also working on another research project looking at how energy management and water quality systems can be used to reduce greenhouse gas emissions. And this is important because as utilities adopt more aggressive greenhouse gas emissions reduction goals, they'll need to understand if and how their operations can support those goals. For example, we currently operate our system to minimize energy costs, but minimizing energy costs doesn't necessarily mean minimizing energy use, and minimizing energy use doesn't necessarily mean minimizing greenhouse gas emissions. Next slide. And with that, I just want to thank you for your time and can answer any questions.
Thanks, Clifford. I want to remind folks that if you have questions, you can type them into the dialog box, which is off the screen to your right. And if you don't see it, you can actually press on the orange arrow on your screen, and the dialog box will pop up. And there's some various things you can do, but you can type questions into that box via the chat function or otherwise. So we're going to do one more poll and then get into the questions. And this poll is related to Clifford's presentation. Specifically, has your water utility performed a detailed analysis of its energy usage or intensity? And has your energy utility performed a detailed analysis of water usage intensity? So if you are a utility, certainly press one of these buttons to select. And if you're not a utility, we'd appreciate you clicking on that one as well. So people are voting, and we're going to give it a little more time. And Joe's going to share the results. And we sort of got this from the first question, actually, that a lot of folks on the phone today aren't affiliated with a water or energy utility, but those who are, it's pretty evenly split there. We've got 13% yes, 15% no, and 10% of folks on the line don't know yet if that's happening. So we're going to go ahead to questions. And a reminder, if you have a question, feel free to type it into the dialog box. But I'm going to start with a question for both Clifford and Suzanne. Thinking about partnerships, because we're talking about partnerships and innovations here. I'm wondering if you can talk about who have been some of the most important partners in getting the projects and initiatives that you talked about today deployed, and the technologies. Clifford, why don't we start with you?
Sure. Yeah. As far as partners, I think in order to make this happen, we both need internal and external partners. Internally, within operations, it wouldn't have been possible unless we had all this SCADA data and all these systems set up. If we didn't have our water conservation group to support us, as well as our IT department, there's a lot of data that we have to get and analyze, and you can't do that without internal support. Externally, we need the electric utilities to be able to provide us all our energy data, in a fashion that's very easy to use. And also, the universities, UC Davis was invaluable. We couldn't have done this work without the universities and their resources. There are a lot of capabilities at your local universities that can help you out with these kinds of studies.
Great. Suzanne, you want to tackle that question?
Sure, Erica, I absolutely agree. I think I would maybe only add a couple of other thoughts. We work with our supply chain vendors to find the most efficient equipment out there and to look at the new technologies that they're bringing to the marketplace. So they've been a tremendous help to us, and those relationships are so important. Also, I spoke a little bit about our innovation development process, and we are always on the lookout for the innovations that are out there. Some of the new technologies that maybe haven't come to the marketplace in a wide reaching application yet. Sometimes they'll come to us, and because of our footprint and how many different utilities we have, how many different systems we operate, we can pilot test new equipment, and so that's been a really good process for us, a pipeline for new technologies.
Great, thanks. I'm going to ask Joe to answer a couple of questions that have come in on the line now. The first one is for Suzanne.
Yeah, so Suzanne, what is your opinion of using VFDs versus combinations of large and small pumps for ramping up and down to meet demand with respect to energy efficiency?
So they both will achieve energy efficiency. And sometimes it depends on the facility that you're looking at. If you're trying to retrofit a facility, you're trying to fit whatever pumps you have in that space, generally. And VFDs are good for that because they don't take up a whole lot of room and they don't involve having to expand the building and do an addition. If you're designing a new facility, I like to have a different selection of pumps depending on your winter pumpage patterns and your summer pumping patterns. It really comes down to an economical decision when you look at what combination of pumps and do you use a VFD. We do both, and it really is very specific to the station we're looking at. Thanks,
Suzanne. Here's a question for Clifford, and I think it picks up on one of your next steps. And the question is, has East Bay Municipal Utility District determined if they will make the investment into coming up with the common data platform? And that questioner is basically asking because they face some of the same challenges in aggregating and analyzing data from a lot of sources. I think they share the big data issue. So yeah, Clifford, I don't know if you might be able to speculate on your guys' future investment or maybe UC Davis's.
Yeah, no, right now we're looking at another research project with UC Davis to look at all of our data and actually partner with some technology companies that handle large data and have cloud computing. So we're looking at ways in which we might be able to deal with these large data sets. It's really not a trivial exercise. And again, I think when you look at the partnerships, this is when you have to bring in additional partners like these large technology companies, whether it's a Microsoft or a Google or an Amazon, to help out because they have the computing power and the platforms to help out. So to answer the question, yes, we are looking at this further, and we're continuing our partnerships to try to solve those problems.
Great. This question can go, I think, to both of you, and I guess, Suzanne, you can take first shot. How have you dealt with the security of and access to water and energy data? And has that arisen as a challenge at all in trying to do, some of the data-driven innovations that you've outlined?
Let me think about that for a minute. I don't think that it has prevented us from doing any of the data analysis or data collection. Generally, when we work with the power utilities, we're working with them on so many different levels, from storm resiliency to emergency response to day-to-day operations. So generally, we're able to share data back and forth. It may be, I won't say manual, but it's not a direct link in terms of computer system to computer system. I think that's probably a challenge in the security sector, but certainly through conversations and data sharing, I have not seen it as a problem.
Thanks, Suzanne. Clifford, I don't know if you have any thing that you'd like to add about the security issues.
Yeah, I think security and the confidentiality, that's actually, when you look at some of the barriers, that is one of the barriers. Coming up with these agreements, especially these three-way agreements between the university, your electric utility, and EBMUD to protect this information and share this information. And when we start talking about bringing customer data and personally identifiable information, that's something that we're actually trying to work through right now between the utility, and the electric utility and the university. We haven't quite cracked that nut. We think we can crack that nut in order to maintain the confidentiality of our customers, but that is a challenge that you have to think about before you go on these projects.
And Joe, I would add, I didn't realize that's what you were referring to, but yes, customer data is very confidential, and there's a lot of rules around that, and we protect that absolutely.
Great. Clifford, your answer was a good segue when you talked about barriers. So that's our next question. What are the biggest barriers you see to doing more in this area? You could speak to policy-wide barriers or technological barriers. You spoke a little bit about agreements and information sharing, but any barriers that you want to speak to?
Yeah, for us, I think the barriers. First the agreements to be able to get the data. That seems once it gets into the legal departments, it goes into this endless loop that consumes a lot of time. The next thing is you have to have the databases and the data available. If you're a utility that you're not collecting all this data, it could be a challenge to start on a project like this. And finally, for us, the last barrier is just resources, and that's where that partnership with the university is very helpful, because we're focused a lot on our day-to-day operations, and to work on these type of projects, which is very interesting and very useful, requires resources that we don't always have. So having those partnerships really helps out.
And Suzanne, maybe you'd like to give your take on what some of the barriers to doing more might be.
I think Clifford, hit a number of them. Resources in terms of we can look at energy usage of all of our facilities, but we have a lot of facilities, right? So typically we're looking at the facilities that use the largest amount of energy and are the oldest facilities. So, it's a matter of resources and prioritizing where you're going to get the most benefit for the work that you do.
Great. Now, I just wanted to, I think, conclude. We're running low on time. To give you guys an opportunity to just say what do you think the next big thing in the water energy space is, either specifically for your operations or kind of for the field at large. And I'll throw out a few ones, whether it be kind of dealing with a particular extreme event like a drought or some significant flooding, or if there might be some technology things that are coming down the pipeline, or maybe some policy things perhaps related to greenhouse gas emissions limitations or other policies that may be in place. Is there anything that's really kind of big on your guys' radar?
Did you want to start, Suzanne?
Sure, I'd be happy to. So I talked about our NP Express patent for a wastewater treatment process. We've been deploying that in our smaller wastewater plants that are about 1 million gallons a day. We are looking at deploying that for our larger facilities, and we think that that has tremendous potential for energy savings. And we're doing some other look on the wastewater side of our business in terms of energy efficiency measures. We are certainly looking at extreme events, hurricanes and tornadoes and what have you, and what the impacts from climate change and climate variability are likely to do to water utilities, and how do we plan for those extreme events. A lot of what we're looking at is in the area of infrastructure investment, and I talked a little bit about the new technologies that are out there for condition assessment of pipelines. And there are several other tools out there for mechanical equipment as well. So we're doing quite a lot of work in that area, and I see that as new tools and techniques come out into the marketplace, they'll help us get more intelligence on our assets.
And I would just go ahead, Clifford.
Quickly add to that, I would agree. I think climate change is going to be a big deal for us. The drought in California is a great example of a challenge that's facing us, as well as if you look at the extreme events across the country. And also, I think Suzanne touched on the fact that infrastructure, we're all working on upgrading or rehabilitating our aging infrastructure. And, and Suzanne had some pipes in the 1800s, and we certainly have pipes in the 1800s at EBMUD. And we might even have a redwood pipe or two as well in the ground somewhere. But, I think infrastructure and climate are going to be huge challenges for utilities going forward.
Great. I want to thank you, Suzanne and Clifford, for not only giving your presentations, but graciously taking all these questions, especially the ones where we put you on the spot. But I think just to kind of summarize, I really appreciated, I think, some of these all of the above recommendations of thinking about technology, thinking about better ways to use your data, thinking about ways to partner with other organizations, that there are a number of tools in this toolbox for approaching water energy issues. And so I really appreciate you sharing your experience. I've just shown on this thank you slide the URL where you can find all the information for this webinar and the previous ones in the series, as well as contact information for myself and Erica. And Erica, I don't know if you have any other closing words?
No, thanks for joining us today, and thanks again for our presenters.